Let's review array expansion. So first off, a little detail about arrays. Arrays have what's called a random access property. So in reality, arrays are just a proxy for your computer's RAM. In case you don't know, RAM stands for random access memory, and the R, the random, is really, really important. Basically what it means is that you can access any location, any index in the array in uniform time. So this is one of our constant time operations. Independent of which particular index we're accessing in an array, we assume that it will take a uniform amount of time. Accessing the first box takes just as long as accessing the middle box or the end box. Okay, so I use a metaphor for this. I kind of think of it as a well-staffed library. So imagine that you've got a library and it's got one librarian dedicated to each book. They're standing there holding their particular book. Okay, not only is there one librarian per book, but there are pitchers. So if you want a particular book, you just call out the call number or the name of the book. The librarian who has that particular book hears you, and they pitch the book to you. It takes a uniform amount of time to access any book because it doesn't really matter where it's located. Okay, so we've got a whole collection of librarians, a whole collection of books, and we've got uniform access independent of location. You ask for the first book, it's pitched at you, gets to you at the exact same time as the last book. Okay, so let's go back to our discussion on arrays. So arrays have some limitations. So arrays have a fixed size when they're created, and that's basically due to how memory is managed. So in order to overcome this, we have to manage our arrays. So a common approach is to create a class. So in Java, there's already an existing ArrayList class that you can leverage. And the class will have methods to manage the array. The methods will do the kind of common operations that you would normally do on an array. So for example, there will be some sort of a get method, and that's equivalent to accessing something in an array and assigning it to a variable. There's a set, which is just the opposite. It's equivalent to assigning a value to a particular location in an array. There's an append, which is equivalent to adding something onto the end of it. And this is where we have to start worrying about the size of our array. Also, often there's a size method that's equivalent to the .length property on Java arrays. Okay, so when we're managing an array, we can separate the notion of the size of the array into two different ideas, into the capacity, which is really like the length of the array. It's how much the array can actually hold. And also maybe some other variable, perhaps n, indicating the actual amount of data in the array at any particular time. Okay, so now we can pick different resizing strategies based on the separated notion of capacity and actual count of contents, capacity versus n. So one of our strategies would be the perfect size strategy. We'll add exactly one space anytime our array is out of space. So the capacity would be equal to n at all times. The other approach that we can take is the doubling approach. So when we're out of space, we could double the capacity of our array. Okay, there are all kinds of varieties in between these two. Instead of doubling, we could triple. Instead of adding one, we could add 4. But essentially, they break down into two broad categories. Either we're adding a fixed constant amount of space every time we're out, for example, just one extra box every time we're out of space, or we're doing some sort of multiple, like doubling the capacity of our array. Okay, so let's walk through kind of a concrete example of several array operations with each of these two approaches. So let's go over an example of the first strategy, increasing the array size by 1. So this square represents my array, and I've just put one value in it. Now on the graph below, the horizontal axis represents the operation I'm doing, the item that's being added, and the vertical axis represents the work. So I've now completed 1 unit of work. To add a second item, I'm going to have to create a new array, copy all my data over, and add my second item. So if we think of the array creation as requiring 2 units of work to create the 2 boxes, and maybe we fill them in simultaneously, we're now up to 2 units of work, and so on. To add my third item, I create a new array, copy things over, add my third item, and I'm up to 3 units of work. And then my fourth item requires creating a new array, copying all of my data over, discarding my original array, and now I'm up to another 4 units of work. and so on with the 5th item, the 6th item, the 7th item, the 8th item. Okay, at this point you probably noticed that this is a lot of work. So now let's try another approach to manage the size of the array. When we run out of space, let's double it. Just like before, we'll start by adding one item, and we'll count that as 1 unit of work. Now we'll go to add a second item. We're out of space, so we'll double the array. It'll have a capacity of 2. We'll add our second item, discard our first array, and we've added 2 more units of work. Finally, things will be different when we go to add our third item. We're out of space, so we'll double the size of our array to contain a capacity of 4. We'll discard our old array, and we've done 4 units of work this time. We're including creating the array in our count of work. So at this point we've done more work than at the equivalent time in the other approach. But when we add in our fourth item, there's already a space for it. So it only requires 1 additional unit of work. When we go to add our fifth item, we're again out of space. So we'll double the size of our array to have a capacity of 8. We copy over our original 4 pieces of data and add in our new piece of data, and we're going to count that as 8 units of work for the 8 spaces in our array. Now adding the 6th item, the 7th item, and the 8th item are trivial. Each one just requires updating 1 position of the array. 1 unit of work each. Once again, our array is full, so to add in the 9th item, we're going to have to double the size of our array to have a total capacity of 16. We'll again copy over the 8 pieces of data that we've already got. We'll add in our 9th piece of data. We'll discard our old array. And now we've done 16 more units of work to create this array with 16 positions. Now to add in our 10th item, and our 11th item, and our 12th item, and our 13th item are each 1 unit of work all the way up until we add in our 16th item. So one of the things that's interesting here is we're essentially building these towers, but the distance between each tower keeps getting twice as far apart. So if you wanted to think about the average amount of work we were doing, you could rearrange these, knock the towers over and flatten them out, and try and get an estimate of the average amount of work being done over those 16 operations. So here you can kind of see a visual depiction of the amount of work that's being done on average. Over our 16 operations, on average, we're doing about 3 units of work each. And that's the real advantage of the array doubling strategy. Sometimes you do a little bit of work that might be strictly necessary, and you might use more space than you absolutely need. But overall, on average, it's much, much faster to add items to the array and grow the array.